So, good morning or afternoon, depending on when you're watching this. Today we're going to introduce the concept of capacitance and talk about a device called a capacitor. Now, the word capacitance sounds a lot like capacity, and that is in essence what we are talking about here. We're talking about what quantity on a conductor determines how much charge you can have on there for a given amount of potential difference. Let me give you an example. Let's say we have two spherical conductors. So I have like this little Van de Graaff generator sphere and this little sphere that I use sometimes with the Van de Graaff generator. Both conductors, both approximately spherical. Now imagine I were to put the same amount of charge on this conductor and this conductor. Which conductor would be at the higher potential? So think about that for a minute. We've got the same amount of charge, say 1 microcoulomb, and I put it on that conductor and this conductor. And remember, the charge is going to find itself on the outside surface of each conductor, and it's going to spread itself evenly. If they're truly spherical, it's going to spread itself all around the conductor evenly. Which of those two conductors is going to have the greater potential? Now, what we have to imagine about conductors and potential, remember, potential is the potential energy per amount of charge in a particular place. So if you bring a certain amount of charge to a particular place, how much potential energy we're giving that system? Well, the closer you bring the charges together, the more potential energy we're talking about here. And so, therefore, the more potential they'll have, the closer together they are. Now, in this big sphere here, the charges can be farther apart. And so they will not store quite as much energy if I were to cram those same exact amount of charges into a smaller space like this. And so the difference between these two conductors, apart from their size, is that this one can have more charge on it for the same potential. Or say another way, for the same charge, it'll have a lower potential energy, so therefore the lower potential. That quantity we're talking about here is called the capacitance. And the capacitance is defined like this. Let me move this out of the way. It's the proportion of the amount of charge you put on something to the potential difference that is created, the potential energy per coulomb of charge, right? The potential difference that is created on that conductor. So it's the amount of charge you put on the conductor divided by the potential that conductor has relative to some reference level. It's that constant of proportionality then that relates the charge and the potential. So the bigger the potential difference you get for a given amount of charge, the smaller the capacitance is. This one will have a larger potential difference for the same charge, therefore it's going to have a smaller capacitance. There we go. Ratio of the amount of charge you put on a conductor to the potential relative to when there's no charge there. That's your capacitance. Now, capacitance is measured in a unit called a farad, named after Michael Faraday. And a capacitor is a device that uses this property of capacitance. A capacitor actually has two conductors. One is at a positive charge, and the other is at a negative charge with the same magnitude. So the net charge in a capacitor is 0. You have two conductors and they each have opposite charges. And so then we would say the capacitance of a capacitor is the ratio of the charge you put on one plate of your capacitor, one of the two conductors, divided by the potential difference between the two conductors. So if you have a positive plate and a negative plate, this is how we often imagine a capacitor to look. It's got two plates. One will be the positive plate and one will be the negative plate, depending on how we charge it up. The ratio of the charge you put on the positive plate, and therefore, but the same magnitude, but negative, the charge you put on the negative plate, divided by the electric potential that exists between the two plates, that's the capacitance of a capacitor. And again, it has to do with the size of the plates for one thing. The bigger the plates, the less crowded the charges are, and the less potential they're going to have for a given amount of charge. The capacitors are quite useful. For one thing, we can store them. It's potential energy. We can store that electrical potential energy. Another thing they're good at is, it turns out that they have a certain frequency with which they will tend to be charged and discharged. And so we can use that frequency as a kind of like a timing device to time how quick something happens. It's very similar to say, a pendulum. You know, a pendulum it can store potential energy. You lift up a pendulum hanging from a string and lift up the pendulum bob, and that stores potential energy. And then when you let go, it releases that energy and turns it into kinetic energy, which can be used some other way. But also, a pendulum has a certain frequency of oscillation, as we've talked about last year in Physics 1. We talked about how certain systems, they tend to oscillate with a certain frequency, and a pendulum is one of those that we talked about, the period of a pendulum. So a pendulum can be used as a timing device, like in a grandfather clock, for example. Well, capacitors are the same. They can store energy, but because it takes a certain characteristic time to charge and discharge a capacitor, they also can be used to do timing functions. So I want you to do a little simulation lab today. I'm going to demonstrate here, first of all, what is actually going on when you're doing the lab. We're going to do a very, very crude version of the lab, but in real life, and then I'm going to have you do the simulation. So the version that we would do involves two metal plates, and the metal plates are just made out of aluminum foil. And I'm going to put the aluminum foil in between the pages of a book. Now, the idea of the pages of the book is to space the metal plates apart a certain distance, but to make sure they don't touch, because the plates of a capacitor aren't supposed to touch, otherwise that's just one big conductor, not two conductors. What we're going to do is we're going to put a known number of pages in between the plates of a capacitor. Right now, I'm going from page 400 in this book to page 420. So that's 10 pieces of paper that are going to be in between the plates of my capacitor. And I'll put the other plate over here. And I need to have a little bit of the plate sticking out of the book. And then I'm going to close it up. And so now I got like a little sandwich made out of the book. You got one conductor here, and then 10 pieces of paper, 10 pages, piece of paper actually, and then the other plate there. And I'm going to measure the capacitance of this setup. This is a device I'm going to use. This is a multimeter that can measure capacitance. Some of them can, some of them can't. So if you ever to do this, you would need a capacitor. You would need a multimeter that measures capacitance. And the way it does it, by the way, it doesn't measure charge or potential or anything. What it does is it actually measures the characteristic time that it takes to charge up this capacitor. That's how it actually does its work. I have it set on like the smallest setting right now in nanofarads, and I'm going to stick this on there. And it looks like it's about 0.4 to 0.5 nanofarads. So farad again is if you have a charge of 1 coulomb on a capacitor producing a potential difference of 1 volt, that's 1 farad. 1 farad is a huge amount of capacitance. So we're talking about nanofarads here. And it looks like we said about 0.5 nanofarads. So now what I'm going to do is I'm going to take my book and I'm going to put about 5 more pieces of paper, 10 more pieces of paper, 20 more pages. So I'll go from 420 to 440. And I'll try to put the little electrode here, little conductor, at approximately the same position on the page. And I'm going to put that together like that. And now we'll see what happens here. So it doesn't change that much. Oh, wait. I don't think I got it to change that much. I might have made a mistake when I put it in there. I might have let the amount that they were overlapping change. Tell you what I'm going to do. In fact, you might have also gone too far once you get the plates too far apart. So I'm going to go the other way instead. I'm going to go from 420. I'm going to go to 410. That way there'll only be 5 pieces of paper apart. Right? And we'll see if that works a little bit better. So if there was about 0.4 before, something like that. And now we're going to put this on there. Yeah, it's 0.9. It's oscillating between 0.9 and 1.0. So that's about double. We reduced the distance between our plates and we actually got an increase in capacitance. Which means that we could have more charge for the same potential difference, or for the same charge we could have a less potential difference is the point. So I want you to do an experiment using a simulation, and the simulation looks like this. Here it is. Oh. Bring it over to that side. In this simulation, and there's a link to this. It's on the coming up page on Canvas. There's a link to a lab. The lab has a link to this simulation. We have a simulated capacitor here, and it has a battery. The battery maintains a potential difference, and so when you establish a potential difference, what happens is charge flows on to the plates of the capacitor, comes out of this battery and flows on to the plates of the capacitor to get the right potential difference. And right now I have these 2 probes from my multimeter hooked up to it. Up here you can select what meters you want. You can have a meter that's a voltmeter. There it is, set that up. And then the plate charge is up here. Now yes, you can just measure the capacitance directly, but I'd rather have you have the experience of calculating the capacitance each time from the charge divided by the potential difference. Not that difficult. So pretend that you don't have the multimeter that has the capacitance setting. You just have the voltage setting in your multimeter. And so what I want you to do is to hook up the multimeter to your plates, and then change your voltage on your battery. That's by moving the slider up. And now I have a voltage of 1.5 volts. That's the maximum voltage. And over here I have a plate charge. It says we're exceeding the scale here. We need to kind of back this out a little bit. There we go. I have a plate charge of 0.13 times 10 to the minus 12 coulombs. So that's one measurement. Now we need to change the features of our capacitor and see how that affects the capacitance. So we would divide the charge, by the way, by the voltage, and that would give us our capacitance. And then we're going to change the separation here. We're going to reduce the separation of our plates by bringing, let's see, can I bring that? Oh, I just changed the area. There we go. I just changed the area of the plate separation of my capacitor by pulling down on this. And when you change the plate separation, it changes the amount of charge for that given amount of voltage. So record those values, determine the capacitance. And what I want you to do is come up with a relationship between the capacitance and the plate separation if you keep everything else the same. Now the other thing you have to keep the same, by the way, is the plate area. Let me get this probe out of the way so I can show you what's going on there. Actually, let me put it over here so it's on there. You can change the plate area. And when you change the plate area, you can see what happens to the charge as you keep the voltage the same. So I want you to get a set of data that relates the plate area to the capacitance if everything else, separation, stays the same. Once you get those data, go ahead and plot some graphs so we can interpret the relationship. And in the lab report, as I recall, it just asks you to come up with a graph, and basically it's a whiteboard item. It's a graph, the linearized equation, the linearized graph, I should say, if necessary, the equation, and the statement of proportionality for both things. So work on that today, and then we will discuss it in the next time we meet. Thank you.